Just a little follow-up to that video from yesterday. At the end of the video I asked if anybody had any clues about how to get rid of this nasty brute force method that I was using, just basically doing a big loop and summing up the durations between steps to figure out how long it would take one of these stepper motors to get up to full speed. And as you can see here, I've got my approximation in there, and this is working pretty well. So I just thought I'd mention a little bit about how I came up with it. This is the series that we're trying to approximate, and I looked at this for a bit and I realized that this xi value, the overall outcome, the summation of this is proportional basically to xi. So if you double xi, you'll double the sum pretty much. So then and actually another clue to that, which I should have been aware of, is that this equation that we're actually trying to approximate with the simplified Taylor version, it actually has the xi value. Well, this is where is it? This xi is the initial value there, c0. So that's actually outside of this whole thing, or this result here is proportional to that basically. There's some square roots in here which will show up in a little bit too, but basically I just sort of did an offline brute force situation where I calculated, or used a spreadsheet to calculate, let's just go back over here a little bit, used a spreadsheet to calculate the first 1,000 terms of this and then their summation. So this column here is just the summation of these two values here, oh sorry, the previous value and the next value in the series. So this is the summation of that, which is the desired value that we want to get. And when I looked at that, it looked kind of like a square root graph, and you can see it over there. This is what I've come up with as my answer. So I drew basically just a square root graph to start with, and then I noticed that it was a little bit low in some places, so I added a little bit more to parts of it, and then I twiddled with this number here. So if I make this to 2, you'll see that the red graph, which is my approximation, is way too high, and if I make it to say 1, then it'll be too low. It's actually not too much too low, but if I put it to this 1.138 value that I had there, for the first 1,000 iterations of this sequence at least, it's very, very close. Like, it's a little bit off. If you zoom this graph in and look at it around about here, it's a little bit off, but if you take the percentage error, so in this column I've just calculated the desired value divided by the approximated value minus 1, so that'll give us an approximate error percentage. So it's about 9% in the very first iteration, but it never gets any worse than that, and it's only about 5% off here, but for most of the rest of the first 1,000 iterations it's less than 1% off. So to look at that, oh, we just looked at it in the code already, didn't we? So that's what I've come up with, and it works great. So there's now no longer any pause between movements, because we don't have to run through this loop for 6 motors to figure out how long they're going to take. We just do that, which is much quicker. I'm using some randomized tests here to make it a little bit more interesting. First one I'll run is just going to do a random 90-degree, random direction 90-degree movement for every motor in sequence. So this is not coordinated, and it's going to be quite fast. So let me just run that one. Actually, this isn't really relevant to this video. It's just it's just kind of neat to look at, so I thought I'd show you anyway. And then I'll do actually this next bit's kind of similar. It's just going to pick a random direction and it's going to move. Why am I doing this? Wait a minute. I think this one's basically the same. It's just going to move more than 90 degrees each time. And because they're all always moving 90 degree in multiples of 90 degrees, they should always end up in one of these, like, you know, north, south, east or west positions like that. And for the last test, which is actually what we came to look at, it's just the same as yesterday, except I've sped up the motors to about as fast as they can go. There's still a slight pause between movements because there's, even though I've gotten rid of that nasty brute force thing, there is still a little bit of preparation that needs to be done. So what this one is going to do is it's going to pick a random set of motors, so each motor has a 60% chance of being included in the movement, and then it's going to do the same thing as we just saw, but it's going to be coordinated, so it's going to be a random multiple of 90 degrees in a random direction up to 4 full rotations at most, I think, is what this is going to do. So anyway, I'll just play this and that'll be the end of the video. This motor is going off for some reason. And that one. So there's still something a little bit odd in here, maybe. Oh no, that one's probably okay, but this motor I've noticed, this is actually the second time I've recorded this, and I didn't want to show you this motor going off because it didn't look cool, so I tried to record it again, but it did it again. So I'm pretty sure it should be about there. Let's try that again, just in case I'm imagining it. Damn, it's going off again, isn't it? Seems to be just this one motor for some reason. I wonder why that is. That's bizarre. Anyway, looks like there's still a little bit of work to be done here. I'll have to swap over the driver that this motor is using and see if the problem switches to another motor. And do a few little tests like that to determine whether it's something actually in my software or maybe it's just an issue with this motor itself. These motors are pretty weak and wimpy, I've found, but not wimpy enough that they couldn't turn this little dial thing. So anyway, that's enough for now. See ya. So I tried swapping the driver for... Oh, did you think this video is finished? No. So I tried swapping the driver for the motor on here to that one, and the problem has now moved to this motor, so it's the driver that is the issue by the looks of it. Might have to try a different driver. I think I have a spare, but it doesn't show up until you do quite a few movements, so I'm going to have to do 20. I'll do one more time and show you. Hopefully the problem will show up on this motor this time. And at the end of that sequence I've put in this bit here, which is a prepare movement for each motor to the negative of its position. So what that will do is it will return the motor to the starting position, which are all north, pointing north at the moment, and that'll give us a better way to judge whether everything, you know, turned back to how it should, return to where it should be. Oh, come on. Looks okay so far. Still looks okay. Damn. It's making a lot of vibrations in the desk. Okay, now they're returning to the north position. There we go. So it's the driver that's the problem. That's really strange, isn't it? Or maybe it's a problem with the this shield that I've got for this Arduino Mega. Maybe it's just sort of not well connected inside the pins where the driver plugs in. Anyway, that is definitely the end of the video now. Thanks for watching. See ya.